thank you for conference. Understand that there are quite a lot of modifications that could be done to the TCP square as we see it over the internet. And in fact, if you look at the TCP square today, and the TCP square to send it over a random path, what are for you the field of the IP header and the TCP segment that are not changed when you send them over the internet. So when you send the TCP packet, what are the fields of the TCP packet that you know for sure will be received without any modification of the destination? The version number. Hopefully the version number will not change. Usually the protocol number will not change. But if you use something else than TCP, UDP, or ICMP, you are unlikely to reach a destination. So it doesn't change, but it doesn't give you much from a usability viewpoint. So it's in this environment that we had to design multipath TCP and extend TCP to be able to use multiple paths to reach a destination, and you will see this has been fun. So now, let's go to the multipath TCP protocol and try to understand how this protocol has been designed and what are the key elements of this protocol. In 2 hours, I won't have time to discuss all the details of multipath TCP, and I will try to address the most important ones. So first, let's look at what was the original objective of multipath TCP. So when multipath TCP was proposed within the IETF, it was proposed as an evolution of TCP. So the multipath TCP working group did not want to change completely TCP and replace it by something else. This has been done before. This is HTTP, and it's cleaner and maybe better than TCP. So what we wanted to do with multipath TCP is that we wanted to have an evolution of TCP which works with unmodified application. So you could take any application which is using TCP today and use this application without any modification to the application. We wanted multipath TCP to work over today's network, which means we want to support IPv4 and IPv6. But saying today's network doesn't simply mean that we need to support IPv4 and IPv6. We need to support any type of pirate box that could exist inside the network, which means that, and this is probably the most important design objective of multipath TCP, is that we wanted multipath TCP to work in all networks where regular TCP works. So if you have a path over the internet where you can open a TCP connection and the TCP connection works correctly, then over this path, we want multipath TCP to work as well. So you know that a TCP connection is identified by IP source, IP destination, source port, and destination port, and that this information is present in all segments. So what do we change to TCP to be able to do multipath TCP? And how do we modify the byte stream model? With multipath TCP, we still have a byte stream between the client and the server. And what we change are the end host. So the end host can have multiple addresses, multiple interfaces. We remove the strong coupling between TCP and IP, and we allow the data to be sent over any path through the network. And that's the main modification we do to TCP. So how do we do that? We look at the protocol in 3 phases. First, we'll have a look at the control plane. So how do we manage a multipath TCP connection? How do we open and close a multipath TCP connection so that it can use multiple paths? Then we'll see how we can transport data. We'll have a brief look at congestion control, and so that we'll have a survey of what is multipath TCP and how multipath TCP works. So first, let's look at how multipath TCP could have been designed in the last century. So in the last century, if we wanted to design multipath TCP, we could have done the following. We are doing an extension to TCP, and any extension to TCP means that when you send a SYN segment, you add inside the SYN segment an option to indicate that you are doing something more than the regular TCP. And the more will be multipath TCP. Then I receive the SYN plus ACK from the server, and I confirm the establishment of the multipath TCP connection. And once the multipath TCP connection has been established, then I can use it to send packets over the blue path or to send packets over the green path. When I was a student, this would have worked perfectly. Does it work today? Let's try to see what's happening when we have middle boxes. So we do the same. I open the TCP connection. I send my first segment over the blue path. And then I try to send a segment over the green path. And this segment is being sent through a middle box, but there is no TCP connection that has been established over this middle box. So for the middle box, since there is no connection, the segment will be dropped. So it means that I open the multipath TCP connection, I have state on the client and I have state on the server, but because I don't have state inside the network, I cannot send additional data over the green subflow. What can I do to solve the problem? To solve the problem, I need to create a TCP connection on the green subflow. If I don't create a TCP connection on the green subflow, there will be no state in the middle boxes, and data will not be able to flow over the green path. So I must create state in the middle box. And this will be done by creating subflows. So a multipath TCP connection is composed of one or more regular TCP subflows, and these regular TCP subflows, they are combined together. And that's what multipath TCP does. Which means that on each host, we will have to maintain state that allows us to glue multiple subflows together, and one subflow which is sent over a single path will appear to the network like a regular TCP subflow so that it can pass correctly through middle boxes. So let's look at multipath TCP now from an architectural viewpoint and to see where multipath TCP fits into the architecture. So we have the application. The application for multipath TCP is unmodified. So it's using the classical socket layer without any modification. So we have the normal socket, and this will interact with multipath TCP. A multipath TCP connection will be composed of multiple subflows. And these different subflows, they will be combined together by using the glue, which is multipath TCP. So multipath TCP is nothing more than, between brackets, a manager of TCP subflows. And the number of TCP subflows that we use to send data is dynamic, and it can change over the lifetime of a multipath TCP connection. So I said, to be able to build a multipath TCP connection, I need to combine multiple subflows, and each subflow must appear as a regular TCP connection. But what is a regular TCP connection? If I look at ITF documents, there is no standard definition of what is a regular TCP connection that would be accepted by middle boxes. So what have we inferred for what is a regular TCP connection for us and for multipath TCP? A regular TCP connection should be a TCP connection that starts with the three-way handshake. And we know that in the three-way handshake, we can use options to indicate that we do something more than the regular TCP. The data segments that we send, they must be sent in sequence. Otherwise, you will have firewalls or TCP normalizers that will block the out-of-sequence segments, so we cannot have gap in the sequence number. And we have to terminate the regular TCP subflow by using fin or reset. So we have these regular subflows. Now, how do we open a multipath TCP connection? To open a multipath TCP connection, we will send a SYN over the first subflow with one option. The server will reply saying that it supports multipath TCP. So now the blue subflow has been established, and I can use the blue subflow to send data. I can also decide to open the second subflow, which will be the green subflow. And to open the second subflow, I will have to use another option to distinguish the second subflow from the first one. And the server will confirm that the second subflow is accepted, will be part of the multipath TCP connection. And then when you have the third act, you have the two subflows that have been established, both for the server and also for the middle boxes that may exist inside the network. And then you can send data over the blue and the green subflow. To be able to do that, I need a way for the client to tell to the server, this green subflow that I'm trying to establish is related to the blue multipath TCP connection, not related to another multipath TCP connection that I have already established with you. So how can I link two subflows together? So how can I link the green subflow with the blue multipath TCP connection? Let's try to see what we could do. First solution is that we know that a TCP connection is always identified by IP source, IP destination, source port, and destination port. So what I could do is that I open the multipath TCP connection. When I open the multipath TCP connection, which is the first subflow, the blue one, I know the source port and the destination port. And when I want to establish the green subflow, I just put inside the green subflow information about the identification of the blue subflow with the IP addresses. And if I provide the information about the port number, I can identify the blue TCP connection, and the server would be able to confirm that this green subflow is related to the blue subflow which appears above. Do you agree with this solution? The problem is always that we have middlebox that may change anything inside the network. And we have NAT, and a NAT will change IP address and port numbers. If we change IP address and port numbers, the identification of the TCP connection that we have is not anymore global. It's only local to the client and local to the server. And an identification which is valid for the client will not appear as the same TCP connection on the server. So I cannot use this port number information to identify the connection. So what do I do? In Multipath TCP, what we do is that we have to use a unique identifier for the Multipath TCP connection. And this identifier for the Multipath TCP connection is called the token. When the client sends the SYN, it will insert inside the SYN the token, which is the local identifier of the Multipath TCP connection on the client. The server will provide its own token number, which will be its local identification of the Multipath TCP connection on the server. Then we do the third act, and when I want to open the green subflow, then I just have to add inside the green subflows options to indicate the token, which is the Multipath TCP connection to which the subflow refers to. And then I can establish the subflow and link it to the Multipath TCP connection. So how can I add subflows to an existing Multipath TCP connection? Well, in practice, I can add as many subflows as I want. The only requirement proposed by Multipath TCP is that on the server, we can distinguish the different subflows. So if we can distinguish the different subflows by using different local IP address, different remote IP address, different local ports, or different remote ports, all the solutions are possible as long as we can distinguish the subflows together. So we have lots of flexibility. We even have in Multipath TCP subflow agility, which means that we can easily add new subflows, we can remove subflows, and we can change the number of subflows. And we might even be in a situation where during some period of time there is no subflow available, and after some time there is a subflow which is becoming available, and we continue the TCP connection. So you could be on a smartphone, you start over Wi-Fi, then you lose Wi-Fi, you don't have a subflow anymore, and 5 seconds later you get back to Wi-Fi and you re-establish a new subflow, and the TCP connection will continue to work without any problem and without any interference for the application, except the fact that during 5 seconds you will not be able to transfer data. So that was for the control plane. So how do we establish a Multipath TCP connection? Now, let's look at how do we transport data over Multipath TCP. So to transport data, let's assume that we have the blue subflow and the green subflows that have been established. So we have the two subflows, and we want to send data over the two subflows. First solution, I send data with a sequence number, and I just send 1 byte at a time so that the sequence number will increment by 1. And you remember that in TCP, we acknowledge the next byte which is expected in sequence, and that's why we acknowledge 124 while we have sent 123. So I could send data over the blue subflow, then data over the green subflow, and again, I just send data over the blue subflow. If I do that in today's internet, it's unlikely that this would work. Because when you have middleboxes will not be very happy to see gaps in the sequence numbering space. And if you have a stateful firewall or a DPI, they will block the TCP connection until you have sent the byte which is missing here. But the byte which is missing here, you have sent it over the other subflow, so it will never come through. That's annoying for Multipath TCP because we would like to be able to send, let's say, half of the data over the blue subflow and half of the data over the green subflow, but we want to do this in a way which is compatible with the middleboxes. So how do we do that? the solution that has been found for multipath TCP is to have, in fact, 2 levels of sequence number. And you will see later on that this is more complex than that, in fact. So the idea is that we have 2 sequence numbers. We have the data sequence number, which is managed by multipath TCP and corresponds to the position of each byte inside the byte stream. And this is called the data sequence number. And then we have for each TCP subflow the regular TCP sequence number, which appears in the TCP segment. And the regular TCP sequence number, which appears in the TCP segment, will be sent in sequence. So how does it work? Now we have, every time we send the data, we have 2 sequence number, the data sequence number, which corresponds to the byte stream, and the TCP sequence number, which is part of the TCP header. So I send the data sequence number 0, and I will get an acknowledgement, first at the byte stream level, and then at the TCP subflow level. And these 2 acknowledgements do not have to be the same. So I can send data over the blue subflow, then I can send data without any problem over the green subflow, because the middle box would only look at the TCP sequence number. The middle box would not know what is the data sequence number. When the data is received by the destination will confirm the reception of the B byte at the TCP subflow level by acknowledging 457, but it will also confirm the fact that the destination has received A and B, and so the data acknowledgement has a value 2. I can send the next byte over the blue subflow. The next byte, which is sent over the blue subflow, has data sequence number 2. The TCP sequence number is 124. For a middle box, there is no gap in the TCP sequence number, and it will be accepted by the middle boxes, and it will be accepted and acknowledged by the destination, and the destination will send the data acknowledgement with a value of 3. So what happens when there are losses? Because TCP is there to provide reliability, so to recover from losses. Basically, what is done in multipath TCP and in the current implementations is that we do fast retransmit and timeouts as in regular TCP at the subflow level. So if you send data over the blue subflow, and for example, the acknowledgement is never received, then there will be a timeout inside the blue subflow that will allow you to retransmit the data in the blue subflow, and once the data is received correctly by the destination, you will get the acknowledgement. It's also possible with multipath TCP that a subflow fails completely. So you are unable to send data over a subflow, typically when you have a smartphone and you lose, for example, Wi-Fi connectivity. When you have sent data over Wi-Fi and then you lose the Wi-Fi connectivity, what could happen is that you will have to retransmit the data over the 3G. So let's see what happens. So I've sent data over the Wi-Fi interface. The data has not been received. After that, I've sent data over the 3G interface. Data has been received by the server, and the server will provide an acknowledgement. What is the acknowledgement that the server will provide on the green subflow? So what is the value of the TCP acknowledgement number, and what is the value of the data acknowledgement that the server will provide over the green subflow? So first, at the TCP sequence number level on the green subflow, the acknowledgement will be for 457 because I acknowledge the reception of byte B. Then, at the data sequence level, I haven't yet received byte 0, so the acknowledgement that I can provide at the data acknowledgement level will only be for sequence number 0. So I acknowledge sequence number 0 at the data level, and I acknowledge 457 at the subflow level. Now, I lose the blue subflow. The blue subflow disappears, and TCP will have to retransmit the data that was initially sent over the blue subflow. So this data that was initially sent over the blue subflow will have to be retransmitted over the green subflow. So it will be retransmitted over the green subflow by using the same data sequence number, because the data sequence number is the position of the data inside the byte stream. This doesn't change. And then I will use the next available TCP sequence number over the green subflow, and this is sequence number 457. The data is received correctly at the receiver. The receiver will now be able to reorder the segments that it has received. So it has received A followed by B, and the data acknowledgement at the byte stream level is 2, and the acknowledgement at the subflow level is 458. So we are able to recover from the loss of one interface and to retransmit data that was initially sent over one interface or over one subflow to retransmit it over another subflow. And currently, the Linux implementation does the following. When it has to do a fast retransmit, the fast retransmit will be done over the same subflow as the one for which it has been transmitted initially. When there is a timeout, the Linux implementation will check whether the data needs to be retransmitted over one subflow or over another, depending on the current quality of the subflow. And if you lose a subflow, you retransmit all the unacknowledged data over another subflow. So flow control, which is an important part of TCP, allows you to adapt the transmission of data to the availability of buffers on the receiver. Two different solutions were investigated in the working group. The first one is to have independent windows on each TCP subflow, and the second one was to have a single window which is shared among all the TCP subflows. So let's try to see how these two solutions work and what are the advantages and the drawback of each of them. First, assume we have independent windows in the TCP, in the different TCP subflows that compose a multipath TCP connection. If we have independent windows, then the advantage is that it's possible to use a window to slow down a sender over one of the subflows. So here in the example, the server is able to slow down the blue subflow by setting a window of 0, and by providing a larger window on the green subflow, then you have the ability to control the amount of data that you receive over the green and over the blue subflow. So this is an advantage of using independent windows. But if you use independent windows, there is a possible problem. So let's look at an example. I've sent data over the blue subflow. Data has been lost. And then I send data over the green subflow, but the server decides that it doesn't want to receive data over the green subflow and set the window to 0. If you set the window to 0 over the green subflow, it means that you do not agree anymore to receive any data over the green subflow. But if you lose the blue subflow at this time, it will be impossible for the client to retransmit the data over the green subflow, and we are in a deadlock between the client and the server. So for this reason, in Multipath TCP, we don't do independent windows. We have a single window which is shared by all subflows, which means that we expect that on the different subflows, the server will always advertise the same window in the different subflows. Which means that we don't have the ability anymore to use a window to control the amount of data that we receive over one subflow versus the other, but you will see that we have other solutions, other techniques to be able to control the data that we receive over a given subflow. Of course, we live in a world where there are middle boxes, so we cannot prevent this from happening. So we could be in a situation where the server is always using a window of 100, but data might be exchanged through a middle boxes that would modify the value of the window. And if a middle box does this, then Multipath TCP will recognize that it should not send too much data there to respect the window which has been imposed by the middle box, but it will know that there are enough buffers on the server if it needs to retransmit data, so that we avoid the problem that I mentioned previously. So Multipath TCP maintains one window, and this is the window between the data sequence number and the data acknowledgement. And the information is always encoded inside the window field of the TCP header. So now that we have seen Multipath TCP and the transmission of data, it's interesting to have a look at how data flows through a Multipath TCP implementation. So we will look at an implementation that interacts with a Multipath TCP implementation, so the application interacts through the socket layer, and we will see what happens when we do a send system call and when we do a receive system call. So when we do a send system call, we will give data to the socket layer. The socket layer will give the data to Multipath TCP. Multipath TCP will divide the data in blocks, and these different blocks will be placed in a queue which is maintained by Multipath TCP. Multipath TCP knows that there are multiple subflows available for this current connection, for this current multipath TCP connection, and multipath TCP will use a scheduler to send the different segments over the different subflows. And there will be one transmit queue which corresponds to each TCP subflow that has been established. So the scheduler is a key part of a TCP implementation, of a multipath TCP implementation, because it allows you to direct the data over the best performing subflow at a given time. So in the current Linux implementation, we will, for example, the scheduler will, for example, favor the connection, the subflow with the smallest round trip time and having an available congestion window, so that we can prefer the subflow with the lowest delay when we are transmitting data. So data is sent over the different subflows. It will be received at the receiver, and inside each subflow, we will have one classical TCP reordering queue, and this reordering at the subflow level will be done by looking only at the information which is part of the standard TCP header. So you look at the sequence number in the standard TCP header to do the reordering, and once this has been done, you push the data which is in order at the subflow level, you push it to Multipath TCP, and Multipath TCP will then look at the data sequence numbers. And based on the data sequence numbers, Multipath TCP will do the reordering and will do the processing of the data acknowledgements as well. When the data is in sequence, you can send it to the application by using the receive system call, and the application does not see any difference between a regular TCP and Multipath TCP, at least through the socket layer. So for Multipath TCP, we need to add more information that needs to be sent between the client and the server. So how do we encode this information, which is the data sequence number, the data acknowledgements, and other types of information which is exchanged by Multipath TCP? In the working group, we evaluated different solutions. The first solution was to change the byte stream, the TCP byte stream, to change the TCP payload and encode the TCP payload as a type length value field. Some would represent regular payload, other would represent control information. If we do that, then the advantage is that we have no limit on the amount of control information that we can put inside the payload of the TCP segment. But the drawback is that your TCP connection, if you look at the payload, if you have, for example, a DPI box that looks at the payload, it will see control information inside the payload. And, for example, an HTTP stream will not appear anymore like an HTTP stream. So it would be a bad idea. The second option is to use TCP option to encode all the Multipath TCP information. This is a solution which has been chosen by the Multipath TCP working group. The drawback of this approach is that the amount of space which is available for TCP options inside TCP segments is limited, because we cannot have more than 40 bytes of options in each TCP segment. So, come back to the measurement study done by Michio Honda and his colleagues that I mentioned earlier. In their study, they tried to see whether it was safe to use TCP options to encode information and send information from a client to a server. And they did measurements by using multiple options. One of them is a timestamp option. So this timestamp option was defined in 1993, if I remember. And they tried to see, when you send a TCP option, a timestamp option inside data, whether this TCP option that you send is received without any modification at the server, or it's modified. So they did measurements by using multiple port numbers. They use 34443, which is a port number which is supposed to be used by nobody, and port 80, which is used by quite many people. And they tried to see whether the timestamp option was modified in both directions, was removed, or was passed without any modification. On a random port, on 4% of the pass, the timestamp option was removed. On HTTP port, there was an error in some cases, or it was modified or removed in 9% of the cases. So when you send packets over a random pass, if you put a TCP option in this packet, you are not sure that the option will reach a destination. And in data segments, you have the same issue than in the scene segments. So it's possible to extend TCP by using option, but you have to know that in some cases it will not pass through. So there is an option format. At the beginning, in the Multipath TCP working group, we had one option for each purpose of TCP extension. So there was one option for the SYN segment to be able to detect, to indicate that we want to support multipath TCP. There was one option for the data segment to encode the data sequence number and the data acknowledgement. In the end, we choose to have a single variable length option. And the reason why we choose to have a single variable length option for multipath TCP is that we did not want to be in a situation where option type 1 is accepted in the SYN, but option type 2 is not accepted in the data segment, because this would have made the protocol even more complex than what it is. So there is a single option in multipath TCP. So how do we transport the data sequence numbers? So we have the TCP segment, the classical TCP header, and we will put the data sequence number inside a TCP option. So how do we do that? So I'm just sending data sequence number, I get the data acknowledgement, data sequence number, and I get the data acknowledgement. So I could put it as a TCP option. What could go wrong if I do that and I send my data acknowledgement and my data sequence numbers inside TCP options? Well, when you send data over any path through the internet, you might get options that are added, removed, or modified in the TCP segments that you send, but you might get some other types of interference. For example, you might, when you send data, and if you send, for example, a small amount of data, you could be in a situation where you send two segments, and these two segments, they are, by miracle, combined together by one middle box. And this middle box would, for example, reduce the overhead that you have for the transmission of the data. And I see someone nodding in the room saying that this could not exist. I guess you have it on your servers. Because when you have servers that do TSO or LRO, this is this kind of middle box. Because you receive multiple segments, and these multiple segments, you combine them together as a single segment. Does it happen on the internet? Does it occur? Yes, of course, and more on HTTP than on a random port number, as usual. So what happens when we have these middle boxes that would coalesce segments for our multipath TCP extension? So I'm sending data with a data sequence number, and assume that this middle box will buffer the small segment, because it wants to minimize the amount of segments that are sent to the server. My next segment is sent over the green subflow. And then my third segment is sent over the blue subflow. And the middle box decides that it has enough data to send one segment that contains both bytes. What will the middle box do? Well, it looks at the sequence number. And from the TCP sequence number viewpoint, the two segments are in sequence. So if you combine A and B together by looking only at the sequence numbers, everything is perfect. So that's what the middle box will do. It will combine the two segments together, so the two payloads together. And for the option, well, the middle box doesn't know the multipath TCP option. So some middle box will keep the last option. Some middle box will keep the first option. If they do that, yeah, we are in deep trouble. If they keep the second option, then we believe that we have received data sequence number 2, which contains A and C. If they keep the first option, we believe that we have received data sequence number 0 and 1 that corresponds to A and C. But 1 has already been received, and we know that 1 is B. So that's an issue. We can also have the same problem with the opposite middle box that would split TCP segments. And if we split TCP segments, we have the issue as well. So when you extend TCP, you have to deal with modification of options, but also with splitting and coalescing of TCP segments. So how can we avoid to desynchronize the client, the state machine on the client and the state machine on the server? Well, the solution which is done and works in multipath TCP is that the multipath TCP option does not contain the data sequence numbers. But it was easy for me to explain you with data sequence numbers. In reality, what you have inside the DSS option of multipath TCP is that you have a mapping between a data sequence number and the difference between the initial and the current subflow sequence numbers. So, because when you send data over the internet, the sequence number that you send, you don't know whether it will be respected at the destination. So the TCP sequence number might change as well. The only thing that doesn't change is the beginning of the byte stream for Multipath TCP and the beginning of the subflow for the byte stream for a given TCP connection. And so you do the mapping between Multipath TCP, the byte stream, and the TCP subflow level. And to deal with the middle boxes that would do coalescing or splitting, we have to indicate for how many bytes the byte stream is valid. So we have to provide the length of the mapping. So with that, we can deal with middle box that would combine segments or split segments. And this works correctly. And this works over the internet, and we've done experiments with the Multipath TCP implementation on Linux that shows that this works. Is it the worst middle box that we have to deal with? Unfortunately not. The worst middle box that we have to deal with in Multipath TCP is the following. So I'm sending data, and I indicate in the DSS option the mapping between the data sequence numbers and the subflow sequence number, and I indicate that the mapping is valid for 2 bytes. The worst middle box for Multipath TCP is a middle box that would insert data inside the byte stream. Yeah, this looks a bit strange, but if you insert data inside the byte stream, then you will be completely desynchronized because the middle box will update the acknowledgement, but it will not update the data acknowledgement, and it will not update the sequence numbers. And the state machine of the client and the server will become desynchronized. So the middle box will always update the sequence number. So for the end host, if you are using regular TCP, this is unmodified. But with Multipath TCP, this doesn't work. But this middle box, is it an academic exercise, or do you know where this middle box exists? Is it invented by people from university to add complexity to Multipath TCP, or is it something real? I guess you have one at home, each of you. That's the old application level gateway for FTP NAT. When you do application level gateway for FTP on a NAT, you have to update IP address and port numbers that are indicated in the port command. And when you update the IP address and the port numbers, these are encoded in ASCII, and you have to increase the length of the payload or decrease the length of the payload, and you modify the content of the payload. And this is the worst middle box that we have to deal with. Multipath TCP works through this middle box, and it's able to detect the presence of this middle box. And if this middle box is on the path, then it will fall back to regular TCP, because we want to make sure that on every path where regular TCP works, we can move to Multipath TCP. So it will work over this path, and we have tested it in the lab and over the internet, and it works correctly with the Linux implementation. So, but to be able to detect that, we had to include a checksum inside Multipath TCP to be able to detect this worst middle box. So in Multipath TCP, we have data sequence numbers. They are used for the data sequence numbers and the data acknowledgements. They are supposed to be maintained as a 64-bit field inside the TCP implementation, but there is a way to encode them in 32 bits or in 64 bits when sending the DSS information. So that's how the option to encode the data sequence number and the data acknowledgement looks like. If you have students and you want to ask them something annoying for the exam, you could ask them what it means. I don't think that's useful today to have a look at it. So we have seen how we can open a Multipath TCP connection. We have seen how we can transport data. Now let's briefly look at how we can do congestion control. I will not spend lots of time on congestion control. You know that in TCP we have the regular additive increase, multiplicative decrease, and that in Multipath TCP, what we do is that we use the losses as an indication of congestion. And when there are losses, in regular TCP, what we do is that we decrease the congestion window so that we avoid causing more congestion in the network and avoid having problems. And this is done by using, when there is a mild congestion, we set the congestion window, we divide it by half, and when there is a severe congestion, then we reset the congestion window to 1 and we restart a slow start. You know how this works. How do we move this to multipath TCP, and what's the difference when we have multiple paths? When we have multiple paths compared to the single TCP path, to the single regular TCP situation, the advantage when you have multiple paths is that if you see losses on one path, then you could send data over the other path. And that's what multipath TCP does intuitively. So if you have one thing to remember about the congestion control of multipath TCP is that the objective of the congestion control is to move traffic away from congested paths. So when you detect congestion over one subflow, then you decrease the transmission rate over this subflow, and you will have the ability to increase the transmission rate over another subflow which is less congested. So multipath TCP gives you the ability to, let's say, select the path where there is the smallest amount of congestion, and we will see examples of that later on. How do we do that? Well, a first solution would be to use independent congestion windows on the different subflows. If I use the regular TCP congestion control over each subflow, then this would be easy to implement, but the drawback of this solution is that we would end up with being unfair compared to regular TCP. Assume that this smartphone is using multipath TCP. It has two paths, while this smartphone is using regular TCP. If I use one congestion control over each path, then there will be a sharing of the common bottleneck so that the first smartphone would get 8 megabits per second, and the second smartphone would get 4 megabits per second. This is unfair compared to regular TCP. And in multipath TCP, what we try to do is that this smartphone would get 6 megabits per second, and this smartphone would get as well 6 megabits per second in this environment. To be able to get this, we change the congestion control so that there is a coupling between the window on the different subflows. And intuitively, the idea of this coupling is that when you see a loss, you should decrease the transmission rate as in regular TCP. But when you have no losses, then you should not grow faster than what a regular TCP connection would do. And this is done by changing the way we compute the congestion window, but this is not that important. So what's important is that you move away traffic from the congested link over the non-congested ones. And as always with TCP congestion control, you will see lots of variants of the TCP congestion control for multipath TCP. So we have seen the basics. Let's go back to the control plane because I have not explained everything about the establishment of a TCP connection. And I've kept the things a bit too simple. So if you look at the multipath TCP control plane, we have to look at how do we establish a connection. We don't have time to do a close of TCP connection, but we'll have a look at how we do address dynamics and how we manage the change of addresses. So let's have a look at connection establishment again. So the principle is that we add a new TCP option which is called MP capable to determine the fact that we are capable of using multipath TCP. This option is placed in the SYN segment together with possibly other options. Then you have the SYN plus ACK, which is returned by the server, and an acknowledgement, which contains as well this option, which is not frequently the case in TCP. And then we can send data over the blue subflow and over the green subflow. So what are the roles of the TCP handshake? We need to propose an initial sequence number. We need to negotiate the maximum segment size, and then we do TCP options. For multipath TCP, what do we do specifically during the three-way handshake? We have to verify that the server is able to support multipath TCP. I said earlier that we need a token to identify each multipath TCP connection. I need to propose a token in the three-way handshake. I said that we are using data sequence numbers. If we want to be secure, these data sequence numbers, they must start with a random number. So we have to propose an initial data sequence numbers. And from a security viewpoint, when a client opens a subflow, I need to check that this client is the legitimate client with whom I'm already talking to. And for this, in multipath TCP, we will be using keys keys that are exchanged in clear. So one issue we had with Multipath TCP is that basically inside the Multipath TCP option, you have to put an initial data sequence number, a token, and a key to do authentication. And this information had to be placed inside 20 bytes. Because the maximum size of the TCP options is 40 bytes. And if you look at the deployed TCP options, we basically already consume 20 bytes inside the SYN segment. So how does it work? The real Multipath TCP connection establishment. So you send a SYN segment. Inside the SYN segment, you will advertise the key, the security key that you will want to use later on to authenticate the establishment of subflows. And this key is sent in clear in Multipath TCP. So you send it to the server. The server will reply by providing its own key. So at this point, the client and the server know both keys. The keys will be confirmed in the third act. And now that we have confirmed the key, we can open a subflow. And to open a subflow, I want to check on the client that I'm talking to the right server, and the server wants to check that he is talking to the right client. And this check will be done by using the keys. So when I open a subflow and I want to link the subflow to the blue Multipath TCP connection, what I will do is that I will provide a nonce, and this nonce will be used for authentication by the server. The server will reply by providing its own nonce and computing a hash map over the random numbers that have been sent, and the keys that are known only by the client and the server. So the server confirms that he is the right server, and the client will later confirm by using hash map that he is the right server as well. At this point, we will be able to use the TCP connection, and the token which I use to identify the TCP connection will be computed from a hash map from a SHA-1 computation of the keys, and the initial sequence numbers will be computed from a SHA-1 computation of the keys as well, to avoid being forced to provide the tokens and the initial sequence number, data sequence numbers in the SYN segment. So last point about the Multipath TCP protocol is the address dynamics. So how does it work? So in Multipath TCP, we are able to support address dynamics. So we can support a server which has multiple IP addresses, IPv4 and IPv6. And we can also support a client which changes its IP address during the lifetime of the TCP connection. So how do we do that? Let's look first at what's happening when you have a multi-home server. So we have a server which has 2 IPv4 addresses and 1 IPv6 address. We first open the Multipath TCP connection, say, for the blue IP address. And once this Multipath TCP connection has been opened for the blue IP address, then the server can advertise the other IP addresses that it owns, so that the client now knows that if it wants to establish a subflow, it can establish a subflow towards any of these addresses that are managed, that are owned by the server. And for example, it chooses to open an IPv6 connection. So at this point, we have a TCP connection that will go over IPv4 and over IPv6 at the same time. If we have a mobile client and say a server which has only 1 IP address, then the same applies. The client starts with, for example, the black address. Then it can advertise the availability of the green address. It can use the green address to create subflows to the servers. And if the blue subflow disappears, for example, because this blue subflow was linked to a Wi-Fi interface, then we can send a special message which is remove address to the server to indicate to the server that it should stop sending data over any subflow which is linked to the 1234 IP address that was used at the beginning. So that's a way to inform the server of the addresses that we have lost. Of course, if we do this in today's internet, we have to deal with middle boxes. So when I open the TCP connections, I could be behind a NAT, and the information that I'm sent as the add address option behind the NAT will be translated by the NAT. So the TCP server, the Multipath TCP server, will not only look at the content of the option, but also the IP address from which the option is coming up. And we solve this issue by using one identifier per address. And when we do an add address to announce an address, we specify the IP address and the identifier of the address. And when we remove an address, we just specify the identifier of the address which is removed. And when we open a subflow, the first subflow is by definition established between the addresses whose identifiers are 0. And then I can add an address with identifier 1. I open the subflow, and when I open the subflow, I specify in what is the identifier of the corresponding address. So that if I need to remove one address, I just remove the blue address. I will send a remove address to indicate that the initial subflow is not valid anymore. So the blue subflow will disappear, and the server will know immediately that it has to send the data over the green subflow. So you can adapt to any changes in addresses. So with that, I think I've covered the basics of the Multipath TCP protocol. Before moving to use cases, I'd like to know whether there are questions in the room. Yes? Maybe use the mic. If you can reach it. But there are many paths to reach the mic.
So does the fact that you're adding subflows happen without any intervention from the application, or is it under control of the application?
So it can happen without any intervention from the application.
So how do you decide?
It's the implementation that decides how many subflows you will establish.
But does that mean that there is some interaction with DNS, or it's purely at the network layer?
So it's purely Multipath TCP. So here, it's Multipath TCP that decides what are the IP addresses that are advertised to the server, and what are the subflows that are used.
Judging from the local IPs?
Yeah, from the local IP,
you.
so it's independent of the DNS. Yeah.
This means the application has to provide information that it wants multiple subflows.
So currently, the application doesn't need to specify that it wants to use multiple subflows. So by default,
how many do you use then? All combinations?
So currently, you can use one per interface, or you can configure the number of interfaces that you want to use on which you enable Multipath TCP. I will have examples later on.
You configure
Yeah,
is in contrast to
so currently,
change to the application.
Currently, it's configured at the system level.
Okay.
So it would be possible to extend the socket interface to have options for the application which is aware of Multipath TCP to specify how it wants to use Multipath TCP. But currently, we assume that the applications are unmodified.
Okay.
One question on the multiple paths. So the client, if it knows that there are multiple paths and I want to use one more than the other, is there a mechanism to specify the priority or how much data should go on each path?
So you want how much paths you want to use?
Yeah, let's say if Wi-Fi is available, maybe I just want to use the Wi-Fi all the time.
So currently it's a system level option. So it's not the application that sets it, but we could extend the socket layer, and the implementation is open source, and you could set for this particular application I want to use multiple paths, and for this application I don't want to use multiple paths. It's just like on some smartphones today, you can say this application can use 3G, or this application can only use Wi-Fi. And this is an extension which could be possible to design.
So in the example there, you show that the added address goes on the wire as an IP address.
Yes, so the add address goes on one of the subflows, because it's a TCP option that goes over one of the established subflows.
So assuming that you use linked local addresses, how can you encode the scope?
If you use?
Linked local IPv6 addresses. So normally you, on the socket API, you have the scope ID field. Some kernels embedded. So do you send embedded scope information?
So currently we don't use linked local addresses inside Multipath TCP.
Okay.
So let's go to the use case now. So I have 3 use cases to show you some experiments that have been done with the current Multipath TCP implementation in the Linux kernel. The first is on data centers. This was initially unexpected to have Multipath TCP in the data centers, but you will see that the results are quite encouraging. The second is on smartphones, and the third is IPv4 and IPv6 coexistence. So first, let's look at data centers. So if you manage servers and you need to increase the bandwidth between servers, and you have, say, 2 servers connected to a switch network, you know that the simple way to increase the bandwidth between the different servers is to add interfaces on the server and to do some form of load balancing. If you use load balancing on the servers, typically what kind of solution can you use today? Well, you have 2 options. You do packet by packet load balancing, so which means you send the even packets on the left interface and the odd packets on the right interface. If you do that, you have a good load balancing at the packet level, but TCP will not be happy because there will be reordering. The other option is to do load balancing at the TCP connection level. So you would identify each TCP connection, do a hash over the TCP connection, and send, say, the even TCP connection on the left interface or the odd TCP connection on the right interface. If you do that, each TCP connection will not be able to use more bandwidth than what's available on one interface. This works. This is used by many people today. With Multipath TCP, what can you do? Well, if you want to increase the bandwidth with Multipath TCP and you are system administrator for a data center, I would suggest you to first use, well, you will use 2 interfaces on the server, but I would encourage you to connect the 2 interfaces to different switches or different spanning trees in your network if you are using spanning trees, so that you have redundancy at the switch level. If one switch dies, then you can use the other one. And then you have the Multipath TCP congestion control scheme that will allow you to use the 2 interfaces at the same time, and it will load balance the traffic over the different interface depending on the amount of traffic which is being sent and depending on the congestion in the network. And Multipath TCP will do this automatically for each TCP connection, and a single TCP connection will be able to use both links together at the same time, and you will see examples later on. Does it work in reality? We did some experiments a few months ago. We received a few good servers on a loan, and on these 2 good servers, we connected them back to back by using 6 10-gig interfaces. So we had a total capacity of 60 gigabits per second between the 2 servers. And what we did is that we used Multipath TCP between the 2 servers, and we used iPerf to measure the bandwidth at the application level. So you will see on the x-axis the time, and on the y-axis the bootput, which is measured by netperf on the server. So we will start with a single interface, and as I mentioned, currently in Multipath TCP, enabling Multipath TCP on one interface is a system level. So we start with one interface, and we are using 10 gig, no surprise. And then, so Christophe, who is there in the room, was doing the experiment. So he will type the command to enable Multipath TCP on an additional interface. So second interface, we get 17 gigabits per second. Now, third interface. So we get 30 gigabits per second. Christophe will enable the fourth interface. So this is bootput measured at the application level by using a modified version of netperf. So we have 40 gig with 4 interfaces. At this point, the machine is getting more and more loaded, and memory bandwidth is becoming a bottleneck. So fifth interface, we are reaching 50 gigabits per second. And then Christophe will enable the last interface. And there we are reaching the limit of the CPU and the memory bandwidth inside the machine. But we managed to get 52 or 53 gigabits per second between 2 applications running on 2 different machines in the lab. So in the lab, you can get pretty good performance by using Multipath TCP, and you can use all the available resources that you have and all the available link bandwidth. So that was in the lab. So in the lab, things work well. What happens in a data center? So if you look at the evolution of data centers, we know that in most data center topologies, we have multiple paths available. Can we exploit these different paths? So going back to regular TCP in a data center, if you look at regular TCP, what happens when you create a TCP connection between one server and another server inside the network? What happens is that since you have massive equal cost multipaths in the network, depending on the identification of the TCP connection, all the packets will follow one path which will be selected by equal cost multipaths. So you send data over this path, it will reach the destination. If you open a second TCP connection inside the network, you might be in a situation where the two TCP connections, they use the same link, and if they use the same link, they will collide, there will be congestion, and you will have to reduce the bandwidth for each TCP connection, although you still have plenty of bandwidth available inside your data center. Because in Ratio, we did this experiment, did some simulations to try to understand what was the optimum TCP throughput in such a data center. And he did an experiment where the optimum throughput was 1 gigabit per second for each TCP connection. And then he did simulations with real TCP and tried to see what is the TCP bandwidth that you can achieve. And the TCP bandwidth that you can achieve in this environment was 200 megabits per second, 400, 500, 600, but most of the time we were far from the 1 gig, the theoretical limit that we were expecting. What was the reason? Well, the reason was that there were too many collisions between different subflows. How can we improve the solution? One way to improve the solution is to say, well, I'm opening TCP connections. Opening TCP connection is like an optimization problem. And I could have an optimizer inside my network. And every time I want to open a TCP connection, I just ask the optimizer what is the best path to create this TCP connection. It will configure static routes in my network, and I will open the TCP connection. And by doing that, I can be sure that the two TCP connections will not collide inside the network. That's a possible solution, but this optimizer might become the bottleneck because it will have to process too many TCP connections. What's the multipath TCP way to solve this problem? Well, I said in the beginning that multipath TCP, we can have different subflows as long as there is an IP address or a port numbers that changes from one subflow to another. So let's configure the server. Although it has a single interface, but it will use two different port numbers, two different source ports when opening a subflow. So when you open a multipath TCP connection, you open it by using two subflows. These two subflows will have two different TCP identification so that when equal cost multipath is used inside the network, it will compute different hash values and it will send the flows over different paths. And if you send the flow over different paths, and you might get a collision, if you have a collision inside the network, yeah, this can happen, this is not a problem, TCP will move away traffic from the congested path. So the black path will get higher bandwidth, and the red path will be unaffected. Does it work? In simulations, so Cosine Ratio did simulations, and this is the blue curve. So when you do multipath TCP, instead of regular TCP, you are able to be closer to the theoretical limit. So this is much better than regular TCP. So in the lab it works. In simulation it works. Does it work in a real data center? That's a measurement that has been done in Amazon EC2 in 2011. Since then, the implementation has been improved. But in Amazon EC2 at that time, we found that between two servers, there were often multiple paths that were available, between 2 and 8. So what we did was the following. So we rented 40 medium CPU instances. We changed the kernel so that it used the multipath TCP kernel. And during 12 hours, what we did was hyperf measurements between the different servers by using regular TCP and multipath TCP with 2 or 4 subflows. So inside EC2, what is the result? On the x-axis, what you have is the measurement for each hyperf experiment. And these are ranked based on the bandwidth that we obtain. And on the y-axis, you have the throughput. Well, the maximum throughput is 1 gig. And there are some results to infer from this figure. First, we don't see that multipath TCP is much better than TCP in this area, which is good because it means that multipath TCP doesn't seem to be unfair to regular TCP, and this area corresponds in fact to machines that were in the same rack. When we did a trace route between the two machines, there was no IP hop between them. On the other path, there were one or several IP hops between them. With regular TCP, we had a bandwidth between 100 and 250 megabits per second. With multipath TCP in 2 subflows, this was better, and with 4 subflows, this was even much better. We tried to discuss with Amazon people, but never managed to get them explain us what was the design of their network, of the data center, or why multipath TCP was behaving like that. So if there are Amazon people in the room and they would like to work with us to understand the performance benefit of multipath TCP in their network, they can contact me. So that was the first use case, data centers. Second use case, smartphones. So we have more and more devices with many wireless interfaces, and we would like to be able to use these multiple wireless interfaces at the same time. And let's do one example, which corresponds to a network administrator, which is doing SSH to his preferred router, which is running multipath TCP. And we have a laptop, and the laptop has 3 interfaces. The first one was Ethernet, the second was Wi-Fi, and the third was 3G. And what we did, so that you can see something, we connected to a server by using SSH, so unmodified SSH, and we ran NIC screensavers on the server so that you can see some kind of video. And during the screensaver, what we will do, so we are connecting to the server. You see the amount of data which is sent over the Ethernet first, because this is the best interface. So data is sent, there is some data over Wi-Fi, then we run the screensaver. And what we will do is that we will disable the different interfaces, and we will see the effect that this has on the SSH connection and the screensaver. So now Ethernet is gone, everything has moved to Wi-Fi. You see there are some hiccups because there are some delays, but the screensaver is not affected beside that. So we disable Wi-Fi. We use 3G now. 3G is slower than Wi-Fi, so the speed of the movement of the screen is much slower, but when we re-enable Ethernet again, all the traffic will move back to Ethernet, and we will send data again over Ethernet. So you preserve your TCP connection independently of the connectivity that you have, and any loss of connectivity will not create a loss for the TCP connection for the application level. And this goes on forever. Then we did measurements of multipath TCP, and we wanted to see what's the best performance with multipath TCP over Wi-Fi. And well, these measurements were done 1 week before finalizing a paper showing that multipath TCP was good. And we said, well, it would be nice to show what's happening on a smartphone. And typical use case for a smartphone was the following: Wi-Fi, 8 megabits per second, 20 millisecond delay. And 3G, 2 megabits per second, 150 millisecond delay. But on the smartphone, we have limited memory. So we wanted to see what's the impact of the receive buffer, the window, on the client on the smartphone. So we first did regular TCP connections. So regular TCP over Wi-Fi works perfectly, 8 megabits per second. And regular TCP over 3G works perfectly as well, except when the receive buffer is really small. But this is not unexpected. This is due to the 150 millisecond delay over the 3G interface. And then we enabled multipath TCP. And we found that. This was a surprising result. So we were expecting that multipath TCP would always get about 10 megabits per second. When a window is large, multipath TCP increases the throughput, and everything works well. But when the window was small, we had, with multipath TCP, a lower throughput than by using regular TCP. This was not a very good selling point for multipath TCP. So we tried to understand what was the reason for this throughput drop inside multipath TCP when you had a limited receive buffer. And after many packet traces, we understood the problem. So we are in the following situation. The client has a limited window. we are sending data over Wi-Fi and 3G. I have some data to send. When I start to send, Multipath TCP will send first, will send over the Wi-Fi and over the 3G, and let's assume that it sends first over the 3G. So data is sent over the 3G, but the data on the 3G is slowly getting to the Wi-Fi. At this point, we've sent everything we could send from the Wi-Fi interface, but the data which has been sent over the 3G interface has not yet reached the destination. And so the sender is blocked because there is data being transmitted over the 3G interface. So how could we solve this problem? The solution is the following. When we detect that Multipath TCP is in this situation, we have the opportunity to transmit over a good interface, but data has been sent without being acknowledged over a bad interface. What we do is that we will re-inject the data from the 3G interface to the Wi-Fi one. Because Multipath TCP allows us to send the data over any interface. And when we do this, then the window is full. We can empty the window and we can continue to send over the blue subflow. And in addition to re-injecting the data, we want to indicate that this is a bad subflow. And so what we do is that we reduce the congestion window by 50% over the green subflow as if there were some losses. So we have a way to penalize the slow subflow. And if we do this change, we get the black curve, which is the curve that you would expect. So when the window is too small, well, there is no miracle. We cannot get more data than the 8 megabits that we could get with Wi-Fi, but when the window increases, we are able to use correctly the available bandwidth. We then ported Multipath TCP on smartphone, and we have a version running on Android. And for that, we developed different modes of utilization of the wireless interfaces. The first mode is the full mode, so we use both 3G and Wi-Fi at the same time. This is what you would do if you had, say, an unlimited plan over 3G. We have backup mode, where we prefer Wi-Fi when it's available, and we open the subflows on 3G, but use them as a backup only. And we have the single pass mode, where only one interface is used at a time, but we can move Multipath TCP connection from one interface to another. We did measurements with this implementation over a real network, a Wi-Fi network, and a 3G network from 2 different providers in Belgium. And we tried to see what's happened and what's the impact on the application when we drop the Wi-Fi interface. That's the only one that we could control. We could not ask the provider to drop the 3G. So on the x-axis, you have the relative time compared to the loss of the Wi-Fi connectivity. And on the y-axis, you have the bandwidth, which is seen by the application, the output from the application. When we use full Multipath TCP, we use both at the same time. We can quickly recover the connectivity and switch back to 3G immediately. When we use the single pass mode, then what happens is that when we detect the loss of connectivity, we have to re-establish the 3G interface, and re-establishing the 3G interface takes about 2 seconds. And once the radio interface is up, but this is related to the modem that we were using, when the radio interface is up, then we need to ramp up the TCP subflow over the 3G interface. But it works, and the application is not affected by the loss of connectivity. Last use case is IPv4, IPv6 coexistence. So we know that IPv6 is coming, and there is a growth in the number of IPv6 users. But we also know that when you look at the characteristics and the performance of paths, that IPv4 and IPv6 do not provide the same performance. In some situations, IPv4 is better than IPv6. In other situations, IPv6 is better than IPv4. And during the lifetime of a long TCP connection, the quality difference and the amount of congestion over the different paths may change during the lifetime of the connection. So what we could do with Multipath TCP is that we could benefit and get the best of both IPv4 and IPv6. Within the ITF, the solution that we have to promote IPv6 today, even if there are parts of the network where IPv6 doesn't work perfectly, is to use IP eyeballs. So IP eyeballs works as follows. You open the TCP connection over the IPv4, and if you don't get a response over IPv6, if you don't get a response quickly, you have a timeout, and you reestablish it over IPv4. and you use the one for which you got a SYN plus ACK, the fastest one. If we want to get the best of IPv4 and IPv6, we could do the following. So we start over IPv6, and thanks to Multipath TCP, we learned the ability of using IPv4 as well on the server. We open IPv4 on the server by joining the IPv4 subflow to the IPv6 subflow, and then we can send data over the best subflow, the one with the lowest delay and with the lowest amount of congestion. So we can benefit from both correctly. So I guess it's time to conclude this survey of Multipath TCP. So I can say that Multipath TCP is becoming a reality. Despite the presence of middleboxes in the network, we have been able to get a protocol which works correctly. So I have to admit that Multipath TCP is more complex than what we initially expected. The RFC has been published in January. There is running code. And the code that exists today is that there is a reference implementation in the Linux kernel. It has been ported to Android. There is a load balancer which has been published by Citrix. There is an anonymous commercial operating system which has reported that they have implemented Multipath TCP completely. And there is an implementation going on FreeBSD. And there will be an interop test between FreeBSD and a Linux implementation this week, while we know that Linux has tested with Citrix has tested with Linux, and the commercial OS has tested with Linux as well. So it works over the rear internet, and you can use it today, at least if you are using Linux. What's next? We could do more use cases with Multipath TCP. You could do Multipath TCP to provide kind of anycast services. Some have been doing virtual machine migration by using Multipath TCP instead of using a VXLAN or whatever technique to hide the change in the IP address. When you do a migration with Multipath TCP, you expose the change of the IP address, but Multipath TCP takes care of the change in the IP address. We could probably use Multipath TCP for storage. And there is time to do improvements to Multipath TCP, because with Multipath TCP, we now, since we have the ability to use multiple paths through the network, the strategies that we have in TCP to do retransmissions, for example, we have to revisit them in the multipath scenario, because now we have multiple paths to be used. We cannot anymore decide when to retransmit data, but we have to decide as well where to retransmit data, which gives another dimension to the retransmission. So you can try it from multipath-tcp.org, and you can download it from multipath-tcp.org. And in the slides that should be available on the IETF website, you will have references to scientific papers, IETF documents, and things like that. With that, I've covered most of what I wanted to cover today. So if you have questions, we have time for some questions before the newcomer introduction.
Do you see any implication in terms of the SPDY or HTTP version 2, or it's totally orthogonal?
So SPDY is application layer.
Yeah.
So if you do SPDY on top of Multipath TCP, it would work like HTTP on top of Multipath TCP. The application is unaware of Multipath TCP.
Thank you.
Hi, I'm Ken Leong. Can you provide more information on due to the middleboxes, the protocol becomes more complex? Can you give some more examples on that?
So what's the problem with the middleboxes? I have to go back to one of the early slides that I mentioned. So the problem with the middlebox is that when you send a TCP segment from the client, you put some data which corresponds to your state machine in the sequence number, the window, the acknowledgement, but the middlebox might change this information without letting you know that they changed this information. And that's the real problem. So what Multipath TCP does is that in most of the case, it tries to be compatible with regular TCP. If it cannot use multiple paths, because there is a middlebox, for example, that would change the content of the payload, then what Multipath TCP will do is that it will fall back to regular TCP. So it will stop using the Multipath TCP extension and behave like a regular TCP connection, so that the connectivity for the application is preserved over this path.
Randy Bourget, IJ. Javier, you uniquely identifying the flow, you kept using multiple V4 addresses, which would be an unpopular sport these years. Can you also get uniqueness by varying the, for instance, source port?
What do you mean by unique source port?
To get the multiples, in your examples,
yeah?
You were using multiple V4 addresses, multiple IP addresses, which would not be very popular and easy these years, and less so. Can you use other things such as source port?
Yes, of course. So that's the Amazon EC2 example. The server were using only one IP address, but different source ports. So you can use as many source ports. You can also use the destination ports as well. This works as well. It's not a good idea for the Middlebox, I agree, but this works as well.
Okay. I would like to go back to the use case that you presented for smartphones.
Yeah.
Basically, what you have usually is like a huge difference between two links, between Wi-Fi and LTE, for example. Have you looked a little bit into the energy efficiency? So, like, what would be the incentive apart from like having this small gain? Because, like, you basically would have like two very different links. And I would say, from user perspective, I wouldn't be interested in having like very tiny gain in capacity if my battery is drained very quickly.
Okay, so when we started this measurement activity, we tried to work with one smartphone vendor to try to see whether it was possible to enable at the same time Wi-Fi and 3G, and what was the energy cost of enabling Wi-Fi and 3G. And it turned out to be really system dependent or version of the smartphone dependent. Mm-hmm. And from a scientific viewpoint, it was very difficult to get data about that. So we did not look at that. Mm-hmm. My expectation is that the best way of using Multipath TCP is to enable only one interface at a time.
Exactly.
There are a few use cases where you want to use both at a time, but if you want to use both at a time, you would like it to work correctly.
Okay, but
from an energy viewpoint, it's better to use only one interface at a time.
But then, if you use just one interface over the time, what is the difference instead of just using regular TCP?
So the difference is that the TCP connection will survive. So,
okay.
So sure. You open your TCP connection, and if you are, say, doing a SSL VPN, you start your SSL VPN, you are currently at home with the Wi-Fi, you move over 3G, you continue your SSL VPN, you go at the office, you continue the SSL VPN, and it's always the same TCP connection.
Sure.
So it's useful for long TCP connection.
Okay. Mm-hmm. Okay, thanks.
Actually, related to this scenario, the question is that I'm on my laptop, if I have 3G and Wi-Fi, normally because of the default route in TCP stack, in the normal TCP stack, I will go to the default route or traffic there. How could we work out in multiple TCP? And also in the IPv6 and IPv4 scenario you just mentioned about, also you, normally the stack will prefer to choose the IPv6.
If you use a classic, you have to do some kind of policy routing to be able to use two interfaces at the same time. And just if you are using Linux, just look at multipath.tcp.org and you will have the explanation on how to enable it on your laptop if you want to test it on your laptop. And for IPv4, IPv6, once you have created the Multipath TCP connection over, say, IPv6, because this is your preferred one, you learn from Multipath TCP the IPv4 addresses, and you can use them.
Okay. So that's integrated into the multiple
that's
TCP.
That's integrated into Multipath TCP.
Thank you.
Yes.
Taiji, is there any security considerations for avoiding the risks for adding the malicious subfloor with the, I think it's related to the hashed value to agree with.
So from a security viewpoint, what we have in Multipath TCP is that we try to not be less secure than regular TCP. So how we do that? And that's not the best solution from a security viewpoint, but if you don't want to change TCP, you don't want to add too much, is that we exchange keys in clear, and we use these keys by using HashMac to authenticate the subflow establishment. Of course, using the keys in clear is not the best solution from a security viewpoint. But if you have 20 bytes, you cannot do Diffie-Hellman in 20 bytes, and you don't want to do Diffie-Hellman for each TCP connection. So there is a trade-off there. There has been an extension which has been proposed, but not yet accepted by the working group, is instead of exchanging keys in clear, when you have an application which is already using keys, for example, TLS, when you are doing TLS on top of Multipath TCP, you could reuse the key which is negotiated by TLS to authenticate the Multipath TCP subflows. And this has been implemented, and it's possible to make it work. But it's not yet accepted by the working group.
Okay. Thank you for a good presentation.
Thank you.
Sorry. Could you go back to the address dynamics page? I'm not sure how it's. Could you explain next slide? And next, sorry. Yeah, this case. So how if there is a NAT between the smartphone and servers?
Yeah.
I'm not sure that still we have an ID using the ID, but
so if there is a NAT, the information that we put inside the TCP option will not be the same as the one that we have in the IP header, because the IP header will be converted by the NAT. It will be translated by the NAT. So I will look at the information in the IP header to learn what is the address. But if it's behind the NAT, it's unlikely to be usable. What's important is to know when this address disappears, and that's why I have an identifier for the address. Because if you look at the remove address, I will specify that I remove the identifier of the address, and I will do the link. So I will know that this one is the blue, and if I remove the blue, then I can remove it. So it's for the removal of the address, which is important to have the identifier of the address.
Okay, so that using the address ID is just for the removing the address. Yeah. Okay.
I guess the last question.
Interoperation with data center TCP and ECN RED, if you actually virtualize over VXLAN. So now I'm actually throwing two branches into Multipath TCP. One, I say, is virtualized, so you have no UDP encapsulation. And second, you're using ECN RED for marking. So how would actually this interoperate in a virtualized data center?
So you want to understand what happens when you do Multipath TCP with RED and ECN?
Yes, indeed. And it is virtualized.
Whether it's virtualized or not doesn't matter, because you will have RED and ECN that would serve as the congestion information for the TCP subflow that Multipath TCP uses, and the TCP subflow will react to ECN. As of today, I don't think that the implementation in the Linux kernel uses ECN correctly, but we could port the ECN implementation that exists in regular TCP so that it is usable with Multipath TCP as well.
So indeed, the point was that ECN, it's apparently not correctly working, particularly if it is in a tunnel. So the insertion and extraction.
Yeah, but then that's an issue with the tunnel and how you do how you look at the ECN bits from the outer tunnel and put them in the inner tunnel.
Okay.
So that's a tunnel implementation.
So you say this would be outside of the multipath.
This should work. It should be possible to change the Linux implementation so that it works with ECN.
Okay.
And then whether it works in a virtualized environment will depend on whether you use the tunnels correctly and you map the ECN information from the tunnels to the TCP segment.
Yes, and finally, you have shown us that the deadlocks caused by the independent reception windows led you to share the window across all of them. Yeah. But then why wouldn't you actually be able to withdraw on a dead connection, unacknowledged, to withdraw and restart on basically on the surviving connections?
Yes, you can withdraw a connection. So if a connection doesn't work well, you could withdraw completely the connection and move the data to the others. But then you lose one subflow.
Yes, indeed.
Yeah.
Yeah. Thanks.
So I guess it's time to conclude. Thanks for attending this tutorial. And I guess there is something planned at 5, if I remember correctly. Thank you.